How is wear rate measured in engineering materials? Imagine trying to figure out how much of a metal part has worn down after thousands of hours of use. That's what measuring wear rate is all about. It helps engineers understand how quickly a material deteriorates under real-world conditions. When machines operate, parts rub against each other, and over time, they lose material. Knowing how fast this happens can prevent unexpected failures and save money. The most straightforward way to measure wear rate is by checking how much mass a component loses during testing. You weigh the part before starting and after completing a wear test with a precise scale. The difference in weight shows how much material has worn away. This method is simple and quick but only works well if you know the material's density. Another common approach is to measure the volume of material lost. This is often more accurate because it accounts for differences in material density. To do this, you can divide the mass loss by the material's density to get the volume lost. Alternatively, surface profiling tools like laser scanners or profilometers can directly map the worn surface. These tools generate detailed 3D images, showing exactly how much material has been removed in cubic millimeters or micrometers. Sometimes, wear is measured by changes in linear dimensions, such as how much a surface's thickness or diameter decreases. Using tools like micrometers or microscopes, engineers can record tiny changes in micrometers or millimeters. This method is especially useful for parts with critical dimensions, like shafts or gears. Once the material loss is known, the wear rate is calculated by relating this loss to the load applied and the distance or time the parts were in contact. For example, you might divide the volume lost by the first pressing the parts together and the sliding distance in meters. This gives a number like cubic millimeters per Newton meter, which helps compare different materials and conditions. Laboratory tests follow standardized procedures to ensure consistent results. The pin-on-disc test is popular, where a pin presses against a rotating disc, and the wear is measured afterward. The block-on-ring test is similar but uses a ring instead of a disc, simulating different types of contact. Abrasive wear tests involve scratching the material with abrasive particles to mimic rough surface conditions. These tests follow standards like the American Society for Testing and Materials G99 and G77 to make sure results are reliable and comparable. For real-time monitoring, advanced techniques are used. Radioactive tracers can be applied to a surface, and as material wears away, the decrease in radioactivity indicates the wear rate. Acoustic emission sensors detect stress waves caused by material loss, while vibration analysis can identify changes in machine behavior linked to wear. Oil debris analysis measures tiny particles in lubricants, giving clues about ongoing wear inside machinery without stopping it. Modern surface profiling tools like laser scanners or coordinate measuring machines can quickly capture detailed images of worn surfaces. These high-tech methods provide precise measurements of wear volume and surface changes, even on complex shapes. They help engineers understand wear mechanisms better and improve material choices. Knowing how to measure wear rate accurately is key to diagnosing why parts fail over time. It helps in selecting better materials, designing longer-lasting components, and planning maintenance before failures happen. By understanding wear mechanisms and how fast they occur, engineers can keep machines running smoothly and avoid costly breakdowns.